Now let's look at a couple of examples. The first one is going to be an example of how to write heat of formation equations, and the second is going to be a Hess's law problem. So I have here the first of the two problems. This is problem 103 out of the end of chapter 9 in your book, and it gives us three compounds and asks us to write balanced equations for the formation of the following compounds from their elements. So in other words, to write out the chemical reaction that corresponds to the heat of formation of the compound. So the three compounds are ethanol, C2H6O. If you don't already know, that is the alcohol in alcoholic beverages, so that's going to be a liquid at room temperature. For part B, we have sodium sulfate, and then for part C, we have the compound dichloromethane, which they tell us is CH2Cl2 and is a liquid at room temperature. So go ahead and try writing down those three, and then once you've tried that, we'll go over the answers together. Alright, so let's look at A, B, and C in that order. For A, we're going to start off with writing the heat of formation equation for ethanol. And for any of these problems, the product of the reaction that we are going to write out the equation for is always going to be just one product, and it's exactly 1 mole of the compound of interest in its standard state at room temperature. So our one and only product of the reaction for the heat of formation for ethanol will be ethanol in its standard state at room temperature, which is a liquid. Now, if we look at the formula for ethanol, we can see that we have carbon in black, hydrogen in blue, and oxygen there in red. So we're going to need to have as reactants the appropriate amounts of carbon, hydrogen, and oxygen as pure elements in their standard states. So we can see that in our 1 mole of ethanol, we have 2 moles of carbon atoms, 6 moles of hydrogen atoms, and 1 mole of oxygen atoms. And so our three reactants are going to be carbon, hydrogen, and oxygen in their standard states. For carbon, the standard state is just carbon solid, specifically graphite. There are other forms of solid carbon, notably diamond, but the standard one is graphite. And we need 2 moles of that. So carbon solid, it just implies 1 mole of carbon, so we'll put a 2 in front of that, and that balances our carbon. Next, we'll want to account for hydrogen. Remember, hydrogen is a diatomic gas at room temperature. So each mole of hydrogen has 2 moles of hydrogen atoms, and so we're going to need 3 moles of H2 to get to our total of 6. So our next reactant will be 3 H2 gas. And then finally we have 1 mole of oxygen atoms. This is going to be slightly tricky because, remember, oxygen is also a diatomic gas, which means that each mole of oxygen comes with 2 moles of oxygen atoms. And remember, for heats of formation equations, we always want there to be only 1 mole of our product no matter what. And so for these equations, we can use fractional molar coefficients. And in this case, we need to use 1/2 to end up with 1 mole of oxygen atoms out of O2. So half a mole of O2 gas will contain 1 mole of oxygen atoms. And so that's our heat of formation equation for the formation of ethanol from its elements. Next, let's look at part B, which is sodium sulfate. Now, sodium, of course, forms +1 cations when it forms compounds, and as you hopefully remember from the polyatomic ion chart in chapter 2, sulfate is one of the most common polyatomic ions. It has formula SO4 and a charge of 2-, and so we're going to need 2 sodium cations for every 1 sulfate ion. And like basically any ionic compound, sodium sulfate will be a solid at room temperature. So we have our formula there, Na2SO4, 2 sodiums to balance our 1 sulfate, in its solid state. And again, there's only going to be 1 mole of that compound on our product side. Now on the reactant side, we have 3 elements in our compound, which are sodium in orange, sulfur in dark yellow, and oxygen in red. So we need 2 moles of sodium, 1 mole of sulfur, and 4 moles of oxygen atoms. And so we want each of those substances in their standard state as pure elements. So for sodium, that's going to be sodium metal, and we need 2 moles of sodium, so we'll put a 2 in front of sodium solid. Next we have sulfur. There's just 1 mole of that, so you could just write that as S solid, and that would be your 1 mole of sulfur in the solid state. If you go look in other references, it's possible that they will be a little bit more specific than that. So technically the standard state for sulfur is S8. So really maybe this should be 1/8 S8, but that's not something that I'm expecting you to know. So on that basis, you could just write sulfur solid and be done with it. And then finally for oxygen, we have 4 moles of oxygen atoms. Of course, oxygen, as in the previous problem, is a diatomic gas, so we need a 2 in front of that to get to our total of 4 moles of oxygen atoms that we have in sodium sulfate. And so the equation that you see here is the balanced equation for the formation of sodium sulfate from its elements. Finally, we have dichloromethane, which is a compound that's used as a solvent in chemistry laboratories. It's also used in paint stripper, so you can actually buy it at hardware stores. And it has formula CH2Cl2, and they tell us that that's a liquid at room temperature. So we have 1 mole of carbon, 2 moles of hydrogen, and 2 moles of chlorine atoms in every mole of dichloromethane. So we want to write out each of those elements in their standard states as pure elements, and we want to be sure that we have the correct number of moles to balance our numbers of moles in 1 mole of dichloromethane. So our first is just going to be carbon solid, again, as graphite. Next we have hydrogen, which is a diatomic gas, so we only need 1 of those to get to 2 moles of hydrogen atoms. And then finally we have chlorine, which is also a diatomic element, so 2 moles of chlorine atoms are in 1 mole of Cl2 gas. And so that's our final equation for the heat of formation reaction for dichloromethane. Alright, hopefully by doing those examples, this is starting to make sense. Let's look at another example out of the end of chapter 9 in your book, which is this problem here, which asks you to find the standard enthalpy change in kilojoules for the reaction of nitric oxide with oxygen, and they show us what that equation is. We have 2 moles of NO gas, which is nitric oxide. Technically, the correct name is nitrogen monoxide, but it's more commonly known as nitric oxide. That reacts with 1 mole of oxygen gas to form 1 mole of dinitrogen tetroxide, N2O4, and all those things are in the gaseous state. Now, they tell us that we have standard enthalpy changes for a couple of reactions there. One is for the dissociation reaction of N2O4 gas into 2 molar equivalents of nitrogen dioxide, NO2 gas, and that has an enthalpy change, a standard enthalpy change of positive 55.3 kilojoules. And furthermore, we have a second reaction where 1 mole of nitrogen monoxide or nitric oxide gas reacts with half a mole of oxygen gas to form 1 mole of nitrogen dioxide gas. And we're told that that has a standard enthalpy change of negative 58.1 kilojoules. So this is a Hess's law problem. Those 2 steps are going to allow us to somehow combine them in one way or another to end up with an enthalpy change that we can associate with the final equation, which, just for emphasis, I'll go ahead and underline that. This one right here. We want to figure out the enthalpy change for that. So this problem might require you to be a little bit creative, especially if you don't have much practice doing these types of problems yet. So go ahead and give this one a try, pause the video, and we'll come back and I'll go over how exactly you can do a problem like this. Okay, so if you struggled with that problem, don't worry about it too much. Hess's law is something that is usually pretty confusing for most people, at least at first, but I think by looking at examples like this, and then of course doing more in the book, and especially for homework, you should get a better feel for how you can end up with an answer to a problem like this. So here I've just rewritten the two individual steps that they gave us, and to make the next couple of steps easier, I've color-coded things. So you can see I've color-coded all the different compounds. N2O4 gas is in blue. Nitrogen dioxide gas I've coded in brown because that compound is actually a brown gas. And then for nitric oxide, NO, that's in purple, and our oxygen is in pink. And I've also, again, shown the enthalpy changes, standard enthalpy changes for those reactions, which are just the same numbers that you see above in the problem. And I've made the first step explicitly positive just to kind of make things a little bit clearer. Now, if you look at those two equations, if we just add them directly together as they are right now, we're not going to get the final equation that we want to end up with. And so what's good to do, actually, is to keep in mind and write down at the bottom of the screen, or the page, I guess, in your case, what the reaction should look like at the end. So the reaction that we want to find the enthalpy change for is shown here. And again, I'm using the same color coding so that we can keep track of things as we go through. Now, what we want to do is essentially rearrange our two equations, or at least potentially rearrange them, and we want to do it so that when they add together, they give us our final equation. Now, the types of things that we're going to need to do for that are, for instance, if we see a compound on the product side in the final result, which in this case that's going to be N2O4, that's going to need to end up on the product side when we add our two equations together. So if we look at that compound, the only place that shows up in our two steps is here in the first step of this reaction. And there's a problem with that compound, which is that it's on the reactant side of that reaction. So we're going to need to adjust that equation. And going through these steps, there's basically two operations you can do to each one. You can either flip an equation, which means transposing the reactants and products, in which case the resulting reaction, basically writing the reaction in reverse, will have the same enthalpy change, except it will be negative if the previous enthalpy change was positive, or vice versa. So you're flipping around the sign. Furthermore, besides flipping something, we can also go through and multiply by some coefficient. So multiply all the coefficients in some reaction by a constant factor, and that will multiply our enthalpy change by the same factor. So in the case of dinitrogen tetroxide, we're going to need to flip that equation in step 1 to end up with a reaction where we have N2O4 on the right side of the equation. And so if we do that, you can see I've just transposed the products and reactants, written that reaction in reverse, and now we have the same enthalpy change as we did above, but it has the opposite sign. So it went from positive 55.3 kilojoules to negative 55.3 kilojoules. And again, the reason we're flipping that is because we want N2O4 on the product side, and it wasn't initially. Now, if we look at some other compounds that show up in our final equation, we have nitric oxide, NO, and O2 gas here in purple and red respectively. So when we add our equations together, we want those two things to be present on the reactant side. And if we look at our second step, we have nitric oxide here, and we have oxygen here. And neither of those things show up in our first equation. So that second equation is not going to need to be flipped around because we have both of the reactants we want on the reactant side. However, we have a second problem, which is that we don't have 2 moles of nitric oxide and 1 mole of oxygen gas on the reactant side in the step 2 equation. We have 1 mole of nitric oxide and just half a mole of oxygen. So what we're going to need to do is if we go through and multiply all of the coefficients in that equation by 2, so let's see, I'll show this in orange. We're going to multiply all of our coefficients by 2 so that this second equation will look more like the equation at the bottom, which is what we're trying to end up with. And so if we multiply that by 2, we're going to need to multiply the associated enthalpy change by 2 as well. So that gets multiplied by 2. And when we do that, our enthalpy change, of course, doubles. And when you go through and multiply your whole balanced equation by 2, you need to make sure to distribute that across all the reactants and products. So we go from 1 nitric oxide to 2 nitric oxides. 1/2 O2 times 2 is going to give us just 1 O2. 1/2 times 2 is 1. And then we have 1 nitrogen dioxide. We're doubling that to 2 NO2s. And so now we have an equation that has both of our reactants on the reactant side and in the correct amounts. And if you look at the two sort of equations that we derived from the original ones, if we now add those two together, we'll actually end up with the reactants on the reactant side, the products on the product side, both in the correct amounts. So we have 1 mole of N2O4 over here. We have 2 moles of NO2 gas here. 1 mole of oxygen gas here. And all of those things are present on the correct sides of those equations in the correct amounts to give us what we have at the bottom. And furthermore, if you look at this compound here, NO2 gas, which does not show up in our final equation, we have 2 moles of NO2 gas on the left side of equation 1 and 2 moles of NO2 gas on the right side of equation 2. And so if we add our modified equations 1 and 2 together, kind of like a spectator ion, if you think back a few chapters, those two things are going to cancel because they're present in the exact same state, in the exact same amount on both sides of the equation. And so both of those things just kind of cancel out like a variable that shows up on both sides of an equation. And so we only end up with our reactants and products in our final equation. And so if we take our modified form of equation 1, which is here, and its associated enthalpy change, and add that to our modified form of equation 2, we'll get the final equation down here. And if we then also add the associated enthalpy changes for those modified reactions, we'll get the enthalpy change for that final reaction. And if we add our two values together, negative 55.3 kilojoules and negative 116.2 kilojoules, we get our final answer, which is negative 171.5 kilojoules. So this is the standard enthalpy change for our final reaction. So that's how you do Hess's law. The big thing to keep in mind here is what you want to do is look at your steps that you were given and try to rearrange them somehow, either by flipping them, multiplying them by a number, or in some cases just keeping them the way they're written, and trying to get each step to look more like our final equation. So with the correct number of moles of some reactant or product on the same side that it shows up in the final equation. And if you do that, then, at least for all the examples we're concerned with, everything else that doesn't show up in the final equation should pretty much automatically cancel out.